In this example, we are given an implicit equation, and we want to find the equation of the tangent line to the curve at the point 1, -2. And we went ahead and graphed this curve for you, so you can see this is an ellipse. We would actually consider it a rotated ellipse. So we're looking for the equation of the tangent line at 1, -2, that would be right here. So essentially, we want the equation for this line. So we know to write the equation for any line, we need to first determine the slope of the line. And that's why we're going to begin by computing the derivative. So we're going to take the derivative of both sides with respect to x. So that's d over dx of everything on the left side, and then d over dx of everything on the right. So this is showing that we're taking the derivative of everything on both sides. And then on the left side of this equation, you'll notice that we're taking the derivative of 3 individual terms. So we know our sum rule with derivatives, that we can take the derivative of those terms separately. So I'm just going to show that here. And this might be a step that you are comfortable skipping initially, which would be fine. But just for clarity, I'm going to show every single step. Now on the right-hand side, we have the derivative of 7, and we know the derivative of a constant is 0, so we can go ahead and just make that 0. So we're taking the derivative of x squared, the derivative of x times y, and then the derivative of y squared. And we're using implicit differentiation to do this. So the derivative of x squared will just be 2x. And then we need to take the derivative of x times y, and we have to really pay attention to the fact that we have a product here, so we need to use the product rule. Now, when we do the product rule, we know we're going to end up with addition because there's addition in the product rule. So it is going to be important that we are going to subtract the entire derivative of x times y. So I'm going to include parentheses here to be sure we're going to subtract the entire quantity. So the product rule says we're going to take the first factor in its original form, which would be x, and then multiply it by the derivative of the second factor. And the derivative of y with respect to x is dy over dx. And remember, that's the same as y prime, and a lot of people will just write it as y prime, but I recommend that you don't use the y prime notation on problems like this, because sometimes when you're in a hurry, you might misunderstand or misread your own work and think this is y to the first power. So I don't recommend that. I recommend that you write it as dy over dx. Plus, the rest of the product rule is the second term, or the second, I should say, factor, which is y, times the derivative of the first, and the derivative of x would just be 1. Then we have the derivative of y squared, which would be 2y, and then once again, the chain rule requires that we chain on the derivative of y with respect to x is equal to 0. So we'll go ahead and distribute our negative and clean this up a little bit. And then at this stage, you'll notice that you have 2 terms that contain a dy dx. So we're going to go ahead and keep those 2 terms on the left side of our equation, and we'll be able to factor out a dy dx. And then we will also take the other terms, basically this 2x and this minus y, and we'll bring those to the other side. So I like to do these 2 steps together to save myself a little bit of time. I'm going to factor out a dy dx from the terms that I have highlighted in blue. So that will leave me with a negative x plus a 2y. But then I'm also going to be subtracting the 2x and adding y to the other side, since those terms do not contain a dy dx. And then this lets me finish up my derivative by dividing. So my derivative will be negative 2x plus y, all divided by negative x plus 2y. Now remember, this is my general derivative, which is going to give me the slope of the tangent line at any point on the given curve. And then if we look back at the original question, we were looking to write the equation for the tangent line at the point 1, -2. So we'll go ahead and then substitute in 1, -2. And this might be a notation you've never seen before, but you are certainly welcome to use, that you can draw a vertical line here, and at the bottom of that vertical line, you can put the point that you're substituting in. And then that's a way to kind of clearly show your work here, that you're notating that you're substituting in x equals 1 and y equals -2. So we'll do our substitution. And then we will also simplify. So we'll have -4 divided by -5, which will get us 4/5. So remember, that's going to be the slope of the tangent line specifically at the point 1, -2. So the majority of our work is done. Our last step is to write the actual equation for the tangent line. And this is where I like to do point slope form. So I would do y minus the y value of my point is equal to the slope of 4/5 times x minus 1. So that would be y plus 2 is equal to 4/5 times the quantity x minus 1. And this is a great answer. This is acceptable. But if you are a person that was wanting slope-intercept form, remember that you can get your slope-intercept form from your point slope form by just distributing. So if we distribute the 4/5, we'd have 4/5 x minus 4/5. And then if we solve for y, we would be subtracting 2. So 4/5 x minus 4/5, and then you have to think that you're going to do a little fraction work. If I'm subtracting 2, 2 over 1 would really be 10/5. So then that would leave me with -4/5 minus 10/5, which is -14/5. So this would be the equation of your tangent line in slope-intercept form, and these are equivalent and they're equally good. And then if you want to go ahead and check that, you could certainly look back at your picture and see if the tangent line that we drew earlier looks like it could be the equation y equals 4/5 x minus 14/5. And you could also open up Desmos and you could graph the ellipse. You could graph our equation that we found and just verify that the equation is indeed a line tangent to the curve at the point given.